Alright, in this video we want to look at absolute extrema, meaning the absolute maximum value of a function and an absolute minimum value of a function. And right now we're looking at these functions on a domain of D. You have an absolute max if and only if f of x is less than or equal to f of c for all x in D, meaning that f of c is the largest value for all x in the domain. You have an absolute minimum if f of x is greater than or equal to f of c for all x in the domain. Again, f of c would be the smallest value. So let's look at A, and let's decide on each one of these. Right, so let's look at the first example. We've got y equals x squared. We've got the graph right here for A. We have the function, and the domain is all real numbers. What we want to find out for each of these scenarios is if the function has an absolute max, an absolute min, both of those, or neither. And so when we look at y equals x squared, we've got the little arrows written in. Okay, so we're talking about the domain of all real numbers, and since this function grows without bound, there is no absolute max value. We do have an absolute min. We have a smallest value, and that absolute min is 0. And it's important to say where it occurs also. So we have an absolute min of 0, and it occurs when x equals 0. In this case, we said there was no absolute max. Now let's look at an example. Instead of having an open interval, let's look at a closed interval. So we've got the same function, y equals x squared, only we're just going from 0 to 2. So let's just look at a piece of this graph. So looking at this graph on the domain of 0 to 2, 0 and 2 are included, I look and I see, is there a smallest y value on this interval? And there is. The absolute min is 0. And again, it occurs when x equals 0. And unlike in the last case where the function grew without bounds, because it was on the domain, negative infinity to infinity, here we have a closed interval, and the maximum value is 4. So an absolute max of 4 when x equals 2. Let's look at C. We have we're looking at the interval we want to look at the interval from 0 to 2, so let's look at the piece of the graph from 0 to 2. Alright, so looking at y equals x squared on a half open interval, we have an open circle at 0, and we have a closed circle when x equals 2, meaning that point is part of the domain, or the interval that we're looking at, but the 0 is not. We're looking here and we want to know, do we have an absolute minimum? And we do not have an absolute minimum. We have an open circle, and for every value that you can think of that's close to 0, we can find one even closer, even less than. So there's no absolute min. There is an absolute max on this interval. The largest y value is 4. So we've got an absolute max of 4 when x equals 2. In the last scenario, we want to look at the open interval from 0 to 2. So we'll have an open circle at 0 and an open circle at 2. And the graph is a little distorted here, my apologies. And so in this case, if you're looking for a local min, there's no local min, nor is there a local max. So in this case, there's no absolute min, and there's no absolute max on this open interval. So when we look at this, we've got on the open interval from negative infinity to infinity, we had an absolute min but no absolute. On the closed interval that was closed on both ends, we had an absolute min and an absolute max. On the half closed, we had an absolute max but no absolute min. And then on another open-ended, we had no absolute max and no absolute min. So this brings us to the extreme value theorem. And what the extreme value theorem says is that if f is continuous on a finite closed interval, then f has both an absolute max and an absolute min. So for a closed interval, the absolute extrema will occur at either an endpoint or a critical value. If you have an open interval, then the absolute extrema will occur only at a critical value. So let's look at the procedure for finding absolute extrema on a closed interval. The first thing we need to do is to find the critical values on the open interval. Right? We find the critical values, which are interior points. We also evaluate f at those critical values and also at endpoints. And then the largest value of f is the absolute max, and the smallest value of f is the absolute min. So we look at example 3, part A. We're first going to find the first derivative. Right. This is a function that we already found the critical values for in the first part, in the last video. So to find the critical values, we set the first derivative equal to 0. We know that 12x squared times x minus 1 equals 0. Our critical values were x equals 0, x equals 1. Now in this example, one of the critical values that we had found on an open interval from negative infinity to infinity technically is not a critical value for this problem because it's an endpoint. We're still going to test it because we test endpoints, but technically for this problem it's not a critical value because it has to be on the interior of the interval that we're looking at. So we're going to test our function at f of 0, f of 1, and f of 5. So I'm going to type the original function in my calculator, 3x to the 4th minus 4x cubed. I don't need to graph it. I just want to evaluate these four values. I can do that using the table feature if I want. I can do it using the home screen. We use the table feature for this. So we want to evaluate at 0. We want to evaluate at 0. We want to evaluate at 1. We want to evaluate at 5. And so at 0, our function value is equal to 0. At 1, it's negative 1. And at 5, it's 1,375. So after evaluating the critical values and the endpoints, we know our maximum value is basically the largest y value on that interval. So this would be the absolute max. We would say the absolute maximum value of the function on this interval is 1,375. It occurs when x equals 5. The absolute min is negative 1. And this occurs when x equals 1. All right, we'll take up the next problem in the next video.